All right, this is 11.3, part 2, and we're about to talk about unit vectors. A unit vector, kind of like a unit circle, unit meaning 1, a unit vector is a vector whose magnitude is 1. And two of the most useful of those are vectors that have a magnitude of 1 in the horizontal and then vertical direction. So if this is 1, and that's 1, one of those vectors, the one in the horizontal direction, has magnitude 1. Looks like that. And we're going to call that vector the I vector. This is very confusing. In math, we use I for lots of different things. Here it's the name of the vector. It does not represent the number square root of -1. So you got to be really careful about that. But the unit vector is called the I vector. And in component form, it terminates at 1, 0. So its component form is 1, 0. And then the one that is in the vertical direction and 1 unit long is called the J vector. And its terminal point is 0, 1. So the component form is 0, 1. And in some courses, you'll see these written slightly differently from how I just did. The notation I'm using right there is appropriate, but a lot of times, because it's a unit vector, in some books you'll see them using this symbol for the unit vector J. It's called J hat, and this would be I hat. You don't have to use that notation if you don't want to. I may slip and use it sometimes, so just to prepare you, that just means it's a unit vector, and it's special. So that's why I'm writing it that way. Okay. So if we have a vector V that in component form is A, B, and let's do an example over here so that this is understandable. Let's make this 2, -3. So if this were vector 2, -3, it would terminate at the point 2, -3. And what I want to think of is, what vectors could I add together that are special unit vectors as defined that would produce that? Well, to get from the origin to that point, using the head to tail method now, if I start at the origin, I could go right 1, right 2. So that's I plus I. Oh, there, you see I did it right there. And then, probably should have done plus. Oh well. Hopefully you'll forgive me. Minus J, minus J, minus J, minus J, minus J, minus J, minus J. Oh, getting ahead of myself. And that would add up to be 2I minus 3j. And so in general, if we have a vector in component form, using unit vectors, that's the same thing as A times I plus B times J. That's our formula for having it, the vector written in terms of unit vectors. Unit vectors I and J. Okay, now let's talk. We've added and subtracted vectors, and we've multiplied them by a scalar, like 3 times a vector. We've done that. Now we're going to talk about how to multiply 2 vectors. There are actually 2 different forms of the multiplication of a vector, only one of which we'll talk about in this course. So the one we're going to talk about is called the dot product, because the symbol used to indicate the multiplication is a dot. The one we're not doing is called the cross product, because that gets into 3 dimensions, and we're not going to do that in this course. The cross product is called that because the vector symbol between them is an X, kind of like regular multiplication symbol from elementary school that you learned. That's called the cross product. The dot product, the one we're going to do, is U dot V. So it's very important you use the correct symbol here, because if you write cross there for a cross product, you should be getting a totally different answer from the one that you will get if you follow this formula. So be very, very careful. All right, so if U is defined in component form as AB, and V is defined as CD, then U dot V, the dot product, is defined as the number A times the number C plus the number B times the number D. And of course, if you multiply numbers and add them together, you're going to get a number. And so notice that the answer here is a number, which we refer to as a scalar. It's just a real number. So the product, the dot product of 2 vectors gives you a scalar, not another vector. The cross product is the thing that gives you another vector. And like I said earlier, that's not where we're going in this course. So every dot product, you should get a number, AC plus BD. And so it's the product of the horizontal components plus the product of the vertical components. If you want to have a word definition, that's how you'd say that. All right, so let's do an example. If we're supposed to be finding the dot product 2 comma 3 dot 4 comma negative 1, then according to this definition we just learned, that's going to be 2 times 4 plus 3 times negative 1, which is 5. Okay, another example, example B. If they're in unit vector form, oh, I'm sorry, got ahead of myself a little bit. So if you have 6I plus 4j, see I'm using the hat. I'll try to use both. I guess I can be a little bit more consistent and try to use both. Dot negative 2I. Of course, once you use it, the hat notation in a problem, you should stick with it. Don't switch halfway through. That just smacks of inconsistency, and maybe you don't know what you're doing. It's still going to be, and you don't have to necessarily write this step, but if you write that back into component form, that's 6 comma 4 dot negative 2 comma 3. But nevertheless, you're still going to take the horizontal scalar number, so the 6, times the other one, -2, plus the vertical scalar, 4, times the other one, 3, and do that arithmetic, and oh, that's 0. Okay. So next we're going to look at the properties of dot product. If you have vectors u, v, and w and real number k, then the following properties are all true for dot product. The dot product of two vectors is commutative, which means that you can change the order in which you write the two vectors that you're finding the dot product for, and you get the same answer either way. The dot product is a commutative process over the addition of vectors. In other words, u dot, the sum of vector v plus vector w, is vector u dot vector v plus vector u dot vector w. Notice I'm not saying times because it is a dot product, so you really want to say that correctly. That dot product and that sum can be in a different order. You could have the sum of two vectors dot another vector, and it's still going to distribute. That's going to be u dot w plus v dot w. If you have a scalar times a vector dot another vector, you can, if you want to, first find the dot product of u and v, and then multiply through by the scalar for that answer. Or if you wanted to, and this is like for convenience, if you wanted to, you could take that scalar to the other vector, find that scalar multiplication of k and v, and then do the dot product u dot that answer. And all three of those would give you the exact same result. Then the next one is if you have a 0 vector dot any vector, the answer you'll get is the number 0. Be very careful. This is always a dot product is always a number. So that 0 I just wrote is the number. Notice there is no vector symbol over it. So be careful about that. And another property of dot product is if you do the dot product of any vector with itself, u dot u, you're going to get the magnitude of vector u squared. Okay. Let me just sort of prove that last one, because that one you may be kind of scratching your head and wondering how that can be so. So if I define u to be ab, and all of these you could do this kind of proof if you wanted to. U dot u is going to be ab dot ab, and of course that's a times a plus b times b according to the definition of dot product, which is a squared plus b squared. Now the magnitude of u, if you'll recall, squared, is going to be the square root of a squared plus b squared. That's the definition for the magnitude of the vector. And if we square that, we get back a squared plus b squared. And so of course, since they're both equal to a squared plus b squared, they must be equal to each other. So I just wanted to prove that. Now, you may be curious as to what the dot product is used for. What does it mean geometrically? What does it mean graphically? And here's where you're going to find it. The geometric interpretation of the dot product. If theta is the angle between the two non-zero vectors u and v, where theta is between 0 and 180 degrees, inclusive, so we won't have any negative angles, we won't have anything bigger than 180 degrees, anything like that, then the dot product of u and v will be the magnitude of u, which is a number, times the magnitude of v, which is a number, times the cosine of theta. Okay, so we've got some vector, say this is u, and another vector, let's say this is v, and this is theta. Then the dot product is going to give you the length of one side of the angle times the side length of the other angle times the cosine of the angle between them. And the version of this that I like a little bit better than that one, although that one's fine, is a lot of times you're using it to solve for theta. So I solve for cosine theta and I commit this to memory. So you'll have the dot product divided by the product of the magnitudes of the two vectors when you solve for cosine theta. So as I just mentioned, this is the one I think I would commit to memory for this. All right. So let's see if we've got an example of that. Find the angle between the two vectors. Okay, so the first problem we're going to do is u is given to be 3, 4, and v is given to be 2, 1. What's the angle between those two things, those two vectors? Well, the cosine of the angle between them will be u dot v divided by the magnitude of u, which is the square root of 3 squared plus 4 squared, multiplied by the magnitude of vector v, which is the square root of 2 squared plus 1 squared. Okay, so 4.21 is 3 times 2 plus 4 times 1. In the denominator, 3 squared 9 plus 4 squared 16 is 25. Square root of 25 is 5. 2 squared plus 1 squared is 5, so that'll be 5 square roots of 5. And that simplifies to be 10 over 5 square roots of 5, so 2 over the square root of 5. And because you're about to put this in the calculator, I would not necessarily rationalize this because it's a calculator active thing anyway. So theta is going to be the cosine inverse of that. Now, I want you to think about what I said about theta and what kind of answer it can be. It has to be a number between 0 and 180 degrees. Well, if you remember when we were talking about inverse cosine, and we were talking about what kind of angles can we have as answers for inverse cosine. Remember, that was anything between 0 and pi, or if we're in degrees, anything between 0 degrees and 180 degrees. So that restriction totally makes sense, because if we do inverse cosine, those are the numbers we'll get every time. So that's kind of a good news idea that it's consistent with what we already did. So if you put that in your calculator, you should get that theta is approximately 26.57 degrees. All right, let's do another example. This is example B. Let's let U be 2, -6, and let's let V be 6, 2. All right, so the cosine of theta will be U dot V over the magnitude of U, 2 squared plus -6 squared, times the magnitude of V, which is 6 squared plus 2 squared. Okay. So let's do that arithmetic. That'll be 2 times 6 plus -6 times 2. Let's see, 4 plus 36 is 40, so that'll be the square root of 40. And that'll also be the square root of 40. Kind of chickened out on you there and didn't simplify because I saw what was coming. And 12 plus -12 is 0. Square root of 40 times square root of 40 is 40. Of course, 0 divided by 40 is 0. So theta is cosine inverse of 0. And that is pi over 2, which in degrees is 90 degrees. And by the way, this is a special result I'd like for you to pay attention to. Those two vectors are at a right angle, and we could have told that. I didn't actually have to do the magnitudes here, and if you see in the long term, that's not really important. If the dot product of U and V is 0, if the dot product of U and V is 0, then this formula will become cosine of theta equals 0, and theta will be 90 degrees. So you can tell if they're at a right angle because their dot product is 0. That's kind of a nice result to keep in your hat. It's kind of nice. So for angles between 0 and 180 degrees, let's see what's possible. And of course, all this relates to the picture I drew up here, so maybe I'll just do this up here. If the cosine of theta is a positive number, that means that the x value on this circle, because remember cosine theta is x over r, that means that the x value must be positive, and that means you're in the first quadrant. And if you're in the first quadrant, that means that theta is an acute angle. Okay? So that cosine theta equals 2 divided by square root of 5 that we did with example A. Since that cosine value is a positive number, that makes sense that 26.57 degrees is acute. It's between 0 degrees and 90 degrees. As we just stated, if cosine of theta is equal to 0, then that implies that theta is a right angle. And if cosine of theta is greater than, less than 0, that means the x value is 0. That means you're in the second quadrant. And that implies that theta is obtuse. So that's kind of good to know and kind of put together as a couple of facts that we can use to our advantage. Okay, next problem. You have a good picture on your notes that you can look at, so I'm not going to try to draw it necessarily unless I need to mark it up somehow. No, actually, I think I'll draw it. So a ship leaves port on a bearing of 28 degrees, and I'm going to go through the drawing with you because I think it's important for you to remember how to do things like bearing and all that stuff. So if this is due north, and this is the port, I'll represent that with the letter P, and travels with a bearing of 28 degrees. Remember, when the bearing is a single number like that, it means clockwise from due north. So I'm going to draw a 28-degree angle from clockwise from north. And that's 28 degrees. Yeah. Okay. And travels for 8.2 miles. So this is 8.2 miles here. Okay. Then the ship turns due east. So now we're going east. And we travel for 4.3 miles. So I'm going to make that shorter. I'm not worried about perfect scale, but I do want it to look shorter. Oh, I just realized that 8.2, I wrote that in a pretty bad place. So let me erase that really fast and put it in a better spot. I should have been looking at their picture. That would have been helpful. This 8.2 miles. Okay. How far is the ship from port? And what is its bearing from the port? So after it's traveled all that way, we're measuring from the port. So from point P, we're going to draw a line segment, and to get direction we'll need to make that a vector, and that orange vector is where the ship is relative to the port right now. And so if we call that point E to match what they did, our question is, how far is the ship from the port? That's going to be the magnitude of vector PE. And the other question is, what is its bearing from the port? Okay. So, with what we know, if I were to sort of draw in this easterly line so that it intersects the north line, we know that the west-east line and the north-south line meet at a right angle. And if this angle down here is 28 degrees, then we can find the angle up there because it's its complement. Or you can use the idea that those three angles add up to 180. So at any rate, that angle that I have in pink is going to be 90 degrees minus 28 degrees. So it ends up being 62 degrees. And then the next angle I want to find is this one. And because the east line is a line, then those two angles, the pink one and the yellow one, must be supplementary. So that angle is going to be 180 minus 62. So that's 118 degrees. Okay. So, since we know the length of the green, which is 8.2, and the length of the red, which is 4.3, and we know the angle between them, we can find the length of PE and the magnitude of vector PE using the law of cosines. So the magnitude of PE, vector PE squared, is side squared plus other side squared minus 2 times the product of those two sides times the cosine of the angle between them. And if you take the square root of that mess on the right side, you end up with a magnitude of, let's see what I wrote down. It's on the next page. About 10.9. And then don't forget to use units. That's 10.9 miles from port. Okay. Now the other question is, what is the bearing? So let's see. To get the bearing, we need to realize that it's going to be measured from north to the PE vector. And since we know part of that is the green angle of 28 degrees, what we need is to find, looking for another color, haven't used yet, I need to find this angle right here. And I can add the green and the turquoise one together to get the gray one, which will give us the bearing. So how will we find that turquoise angle? Well, we can use law of sines to do that. We know that the sine of that turquoise angle, what should I call that? Let's call that theta. So we haven't used theta yet today in this problem. So the sine of that angle over the opposite side, which is 4.3, should equal the sine of 118 degrees divided by the side opposite it, which is the distance we just got. So instead of typing 10.9 in a minute for this, you should have stored that 10.9 number in your calculator. And although I'm writing 10.9 on paper, you really want to make sure that you're using the calculator stored value, as we talked about earlier. So to solve for sine, I'm going to multiply both sides by 4.3. Then to solve for sine, to solve for theta, I'm going to take sine inverse of both sides. And this is the calculator ready form. Make sure that you use your stored number for 10.9. Do not type 10.9 in again, because that's not quite right. It's a rounded value. And so that angle should be about 20 degrees. So the gray angle which is the bearing, will be the green angle that we were given, 28 degrees, plus the turquoise angle that we just calculated approximately. And so the bearing is approximately 48 degrees. Okay. Next problem. In air navigation, the airspeed of a plane is its speed relative to the air, and the ground speed is its speed relative to the ground. Because of wind, these two speeds are usually different. I think of airspeed as like the speed it's trying to fly at, but if the wind is blowing, it might not be going exactly that speed. For example, if it's trying to go, I'm going to make up numbers, they probably won't make sense. Let's say it's trying to travel at 1,000 miles per hour, and it's got a tailwind of 100 miles per hour. Well, it's effectively going to be going 1,100 miles per hour. If it has a headwind of 100 miles per hour, it's going to effectively be moving at 900 miles per hour. Then if it's at any other angle besides same direction as the plane or opposite direction of the plane, it's a little bit more complicated. So I think you have this picture in your notes. What you're trying to do is you're trying to fly at this angle and speed, represented by this vector. So you might think of that as the setting for the bearing and speed that we want, called the airspeed. That's what we think we're doing, and if you neglect wind, that's what we would be doing. Now, if you have a vector that's a wind that's pushing at it, let's say kind of from the right, sort of, but a little bit north as well, so it doesn't really matter. I can draw that vector here if I want to. Remember the head to tail method. You can draw that vector anywhere, have it point at the plane itself, but this will work. It's the same thing. So this is the vector for the wind direction and the wind speed. Okay, and then the result, what will actually happen is that we'll go at this direction at the speed indicated by the magnitude of that red vector. And so this is your final bearing. It's what you actually end up doing. And ground speed is what we call that actual speed that we're actually moving. Okay, so that's how we're going to calculate these resulting, what's the plane actually doing. Right, so let's do a problem where we use that idea. I think you have this picture, but if you don't, it's probably a good idea for you to learn how to draw the picture regardless. So I'm going to pretend like you don't have the picture. A plane with an airspeed of 192 miles per hour is headed on a bearing of 121 degrees. Okay, I'm going to draw this over here. So that's supposed to be due north. And it's flying at 121, is headed on a bearing of 121 degrees. So we're going to go clockwise. 90 is that far, plus another 31. It's about right there. And the magnitude of that is 192 miles per hour. So the magnitude is the speed. So the length of that is relative to what kind of speed you're doing. The longer, the faster you're going. Okay, so that's the first piece of information. A north wind is blowing, that is from north to south. So we have a little vector that does that. And a lot of times you draw this a bit exaggerated, not to scale, just basically so that your drawing makes sense and you can see stuff. So the wind speed's generally not very big compared to the speed of the airplane. And in fact, in this case, it's 15.9 miles per hour. So it's definitely shorter than 192, but that's probably not drawn to scale. Okay, then we're supposed to find the ground speed and the actual bearing of the plane. So we're looking for the resultant of those two forces being added together, which would be that vector. Okay, so let's call this vector v. That's our answer vector. And our question is, what is the magnitude of v and what is the bearing of v? Those are our two questions. All right. So let's see what we can figure out here. Oops, don't want to get rid of my picture. I did want more room to work. Ah, well, that's all right. Let's see. Well, there's an angle. Let's see. Let me think about this a second. Oh, yeah, we've done this a couple times. It was staring me right in the face. The magnitude of v, we can use the law of cosines to find that. So 192 squared, 192 squared plus 15.9 squared minus 2 times 192 times 15.9 times the cosine of let's see. Yeah, it's 121 degrees. Because that's 121 degrees because this angle right here is congruent to that one. And let me tell you what was going through my head. If you have parallel lines, which the north-south direction and the wind are parallel to each other, cut by a transversal, then this angle here, which is the original 121 degrees, is congruent to this angle here. Alternate interior angles are congruent. And that angle, of course, is the angle that's across from the magnitude of v that we're trying to find. So that's why that goes there. And let's see, you do the calculation by taking the square root of that mess on the right, and you should get about 200.7 miles per hour. All of our magnitudes of our vectors are in miles per hour in this problem. Okay. And you'd want to store that in your calculator. Now, to find the bearing, we're going to need to find the angle here. And add it to the pink one to get our bearing, which will be that angle, whoops, that angle. So gray angle will equal pink angle plus red angle. Of course, the pink one we know is already 192. We need to find that red angle. So, because we do know the angle and opposite side pair for V, we can use that. So I'm going to call this angle inside of here, this little red one, temporary. I'm just going to call it alpha. So the law of sines says that the sine of unknown alpha divided by the angle of the side opposite it, which is 15.9, should equal the sine of any other known angle in the triangle. So that's the 121 degree angle divided by the side length opposite it, which is that 200.7 number, which you'll not type that exactly. You'll use what's stored in your calculator, of course. And so multiplying both sides by 15.9, we'll get that sine of alpha is 15.9 times the sine of 121 degrees divided by that stored in the calculator number. And so alpha will be sine inverse of that mess. Which ends up being about 3.89 degrees. So the bearing, consequently, is equal to the pink angle, which is the 121 degrees. Oops. That we were given at the outset, plus the angle we just found, 3.89 degrees. And so the bearing is about 125 degrees. A little bit more precision, it's 124.89 degrees, but it's about 125 degrees. Okay, so it looks like we've run out of room on this one, so I'm going to have to go to another recording for the very end. So I'll see you later.